Hello, today we are learning about the trapezoidal rule. So in last lesson what we learnt was how to approximate area under the curve using rectangles, triangles, squares and trapeziums. So a trapezium usually gives a much closer approximation to the area under the curve than a rectangle does, or of any of our other shapes. So what we do is we use the trapezoidal rule, which is a formula that uses a trapezium to find the area under the curve, or multiple trapeziums or trapezia. So the general rule for the trapezoidal rule when using subintervals or trapezia, which are our strips of area, is used by, given that we have n subintervals or trapezia or strips, we have the integral of a to b of fx dx is approximately h on 2 of the function a plus the function at b plus 2 lots of the function at x1 plus all the way up to the function of x n minus 1. This is where we have a equals x0, b equals xn, and the values x0, x1, x2, all the way up to xn are found by dividing the interval of a is less than x is less than b into n equals sub-intervals with the width of h equals b minus a all over n. So since we know that b minus a all over n, we can use this formula. Now this formula here is the formula that is on our reference sheet at the bottom of our integrals. So it's really important that we have a deep understanding of it. So we have the integration of a to b of our function dx is approximately, now instead of the h we substitute in our b minus a all over 2 times our n of our function at a plus our function at b plus 2 lots of our function at f of x1 all the way up to our function of x n minus 1. So our trapezoidal rule summarized is b minus a over 2n of our first plus our last plus 2 lots of everything else. So it's also very important that we note that 4 trapezia equals 4 subintervals, which equals 5 function values. So when we're working out what our function values are by using a table a little bit later on in our examples, in our tables for our 4 trapezia, we'll have 5 function values. So our first example is to use the trapezoidal rule to find an approximation for the integral of 1 to 5 of 1 on x dx. So what we have here is when we haven't been told any subintervals or trapezia, it means that we just have one subinterval, one trapezia, one strip. So no identifying of how many subintervals means that n equals 1, meaning that we only have one subinterval, one trapezia. So now it's also very important to identify what our a, our b value is, and what our fx is, as well as our n value. So we're going to write, therefore, our a is our number down here, which is our 1. Our b is the top of our integral, which is 5. Our function in this case is 1 on x, and we know that our n equals 1. So we can now substitute these values into our trapezoidal rule. So we have our trapezoidal rule of a, which is 1 to 5, of 1 on x, which is our function of dx, is approximately equal to b, which is 5, minus a of 1, all over 2 lots of n, which is 1. And then what we do is we want to find f of 1, which is our a, plus f of 5, which was our b. And because we don't have anything else, we don't worry about our 2 lots of fx, 1 plus all the way up to fx n minus 1. So what we want to do now is we want to draw a little table over to the side. And in our table, what we want to put in is, we only need 3 columns for this, is when whatever our x value is, what our f of x is. So we have x values in this case of 1 and 5. So when we sub in 1 into our function, what we get is 1 over 1, which equals 1. And when we sub 5 into our function, we'll have 1 over 5, which equals 1 over 5. So we can now substitute these values in for our f of 1 and our f plus 5. So we'll have this equals 5 minus 1 is 4 over 2. Lots of f of 1 is 1 plus f of 5 we know is 1 over 5. So 4 divided by 2 is 2, and 1 plus a fifth is 6 fifths. So 2 times 6 fifths is 12 over 5. And so that's our approximation of our area using our trapezoidal rule. Our next example, what we have is the integral of 0 to 1 of x cubed dx using 2 subintervals. So because we have 2 subintervals, what that means is that we are going to have 3 function values. Okay, so equals 3 function values. And therefore our n will equal 2. So our n equals how many subintervals we have. We then need to identify what our a is. So a equals 0, b equals 1, and our f of x equals x cubed. And we know that our n equals 2. I'm just going to write that again. So what we're going to do this time, instead of going straight into our formula for the trapezoidal rule, is we are actually going to look at our table first. So we need 3 function values or 3 x values in our table. So we need our first, our last, and we need a value directly in the middle. So directly in the middle would be 0.5. So when we sub 0 into our function, we'll have 0 cubed, which is 0. When we sub 0.5 into our function, 0.5 cubed is 0.125, and when we sub 1 into our function, 1 cubed is 1. So now that we know these values, we can look at our trapezoidal rule. So it is 0 to 1 of x cubed dx is equal to b minus a. So b is 1 minus a of 0 all over 2 lots of n. So 2 times n of our function, our first, so that's f of 0 plus our last, f of 1 plus 2 lots of everything else. So 2 lots of f of 0.5. Okay, so 1 minus 0 is 1 over 2 times 2 is 4. F of 0 is 0 plus f of 1 is 1 plus 2 lots of f of 0.5 is 0.125. Okay, so 0 plus 1 plus 2 lots of 0.125 is just equal to 1.25, and that multiplied by a quarter is equal to 0.3125. Okay, our next example says to use the trapezoidal rule with 4 subintervals to find an approximation for the integral of 2 to 3 of 2 over x minus 1 dx, correct to 3 decimal places. So we have 4 subintervals. So that means we're going to need 5 function values in our table. Okay, so identify our A. Our A is 2, our B is 3, our function is 2 over x minus 1, and our n is how many subintervals we have, which is 4. Okay, again, we're going to go straight into our table. Okay, so we need 5 function values, so that means we're going to need 6 columns. 3, 4, 5, 6. Okay, our f of x. So our lowest number is 2, or our first number is 2. Our highest number is 3, and then we need even intervals in between. So we're going to have 2.25, 2.5, and 2.75. So when we sub 2 into our function, we get 2 over 2 minus 1, which is 2. When we sub 2.5 into our function, or 2.25, sorry, it's our next value, we get 1.6 exactly. When we sub 2.5 into our function, we get 1.3 repeater. Now I'm going to store this in my calculator as A, so shift recall A, because we will substitute that in later on. Then when we sub in 2.75 into our function, we get 1.142857143. So I'm going to store this into my calculator as B. Okay, so shift recall B, and then when we sub 3 into our function, we get it equal to 1. So if we look at our trapezoidal rule now, so the integral of 2 to 3 of 2 over x minus 1 dx, what we get is we get b minus a, so 3 minus 2 over 2 lots of n, which is 4, and this is multiplied by our first, so function of our first plus our last plus 2 lots of everything else. Now this line is still extremely important that we write down to show our understanding. And that's a square bracket, lots of brackets going on. So 3 minus 2 is 1 over 8, and then we know that f of 2 is 2, plus f of 3 is 1, plus 2 lots of f of 2.25 is 1.6 exactly, plus f of 2.5 is 1.3 repeater, plus f of 2.75 is 1.14 ... Okay, and it's extremely important to show this substitution. So then we have 1 of 8, and then we need to add all of this together, remembering that our 1 of 3 is A, and our 1.14 continued is our B value in our calculator. So when we put this into our calculator, we get 11.1523895, and we need to multiply that by an eighth, and when we do so, we get 1.394047619. So that equals, correct to 3 decimal places, 1.394. Now make sure that you write out whole calculator screen to show correct rounding, because if you make a mistake, you will lose a mark in an assessment task. Now when we're talking about the approximation, we're talking about the approximation of the area under the curve, so we really should be writing units squared at the end of our examples. So just go back and do that for me. Okay, example 3, we want to use the trapezoidal rule with 7 trapezia to find an approximation for 0 to 14 of t squared plus 4 dx. So can we change that dx to a dt because it's in terms of t. So what we have is we have 7 trapezia, which means we'll have 8 function values when we use our table. Okay, so we have A is equal to 0, our B is equal to 14, our function, or f of t in this case, is equal to t squared plus 4, and we have the n is equal to 7 because that's how many trapezia or sub-intervals we have. We need to do up our table next. Okay, and just remembering with our table we need 8 columns in here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, Okay, where this is our x, this is our f of x, or sorry, it's our t in this case. Oops, did not mean to rub that all out. So we'll have our t, our smallest t, oops, will be 0 and then 14, and then we need even intervals in between. So this will be going up by 2s. So 2, 4, 6, 8. Whoops, that doesn't work. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh, because we need another one. That is why. Okay, so it's really important that we make sure that we draw enough columns. So 6, 8, 10, 12, 14. Okay, so now we need to sub these t values into our function. So 0 squared plus 4 is just equal to 4. 2 squared plus 4 is 8. 4 squared plus 4 is 20. 16 squared, 6 squared. 6 squared plus 4 is 40. 8 squared plus 4 is 68. 10 squared plus 4 is 104. 12 squared plus 4 is 148. And 14 squared plus 4 is 200. Okay, so now in our trapezoidal rule we have 0 to 14 of t squared plus 4 dt is approximately b, which is 14, minus a of 0 of 2 lots of n, which is 7, of f of the first one, so f of 0, plus f of 14, plus 2 times everything else. So that's f of 2, f of 4, f of 6, plus f of 8, plus f of 10, plus f of 12. Okay, so now we need to substitute our numbers in. So 14 divided by 14, and then we have 4 plus 200 plus 2 lots of 8 plus 20 plus 40 plus 68 plus 104 plus 148. So 14 divided by 14 is 1. Lots of 4 plus 200 plus 2 lots of 8 plus 20 plus 40 plus 68 plus 104 plus 148 is 980. So this will equal 980 units squared. And finally, our last example is that a surveyor needs to find the area of the irregular piece of land shown, and we want to use the trapezoidal rule to find its approximate area. So we're going to find the area of each trapezoidal, and so we have 5 here. Okay, so we need to use the values in our diagram, or we can put them in our table. So we have how many? We have 4 trapezia, which equals 5 function values. So we're going to have 5 function values in our table. So that means we need 6 rows. 6 columns, sorry. 6 rows could be a bit much. 2, 3, 4, 5, 6. So that will be x, fx. And it will be 0, 1, 2, 3, 4 will be our numbers. 0, 1, 2, 3, 4. Okay, and we have what our fx match up to be, and they are our lengths there. So our 3.7 matches up with 0, 5.9 with 1, 6.4 with 2, 5.1 with 3, and 4.9 with 4. So using this, we therefore have that A is 0 because it's our smallest, B is 4, and our N is also equal to 4 because we have 4 areas here, or 4 trapeziums. So we can substitute this into our trapezoidal rule, and instead of writing our integral, we're going to write area equals, and so it's going to be b minus a over 2n of f of a plus f of b plus 2 lots of everything else. Okay, so our b is 4 minus our a is 0 over 2 lots of 4, and we have f of a is 3.7. Oh, we're going to actually write this out as f of 0 plus f of 4 plus 2 lots of f of 1 plus f of 2 plus f of 3, lots of brackets, so we'll have 4 over 8 lots of 3.7 plus 4.9 plus 2 lots of 5.9 plus 6.4 plus 5.1. And so then we'll have a half times 3.7 plus 4.9 plus 2 lots of 5.9 plus 6.4 plus 5.1. Oops, needed decimal point there. And that equals 43.4. So a half times 43.4 equals 21.7. So therefore the area of the land is approximately 21.7 meters squared. And that